Let's look at how Snowflake has evolved over the past decade. When Snowflake came out of stealth mode after 2 years, their second CEO described their product perfectly as the database that reimagines data warehousing as a cloud service. The first name of their product was the Snowflake Elastic Data Warehouse, and they often use the term data warehouse as a service. Fast forward to 2023, and each new Snowflake press release hits different. This one is about how you can create generative apps by fine-tuning large language models with your own Snowflake data. Times sure have changed, so let's track the progress. A press release like this conforms to a standard format. A location and date is followed by the company's name and a short description of how they want to be thought of. For example, Confluent calls itself the data streaming pioneer. Zscaler is the leader in cloud security, and Nutanix is a leader in hybrid multi-cloud computing. When the company was named Snowflake Computing, its descriptions were all about data warehousing. The Cloud Data Warehousing Company, the data warehouse built for the cloud, and the only data warehouse built for the cloud. But once they dropped computing from their name, Snowflake started to describe itself as a platform. The Cloud Data Platform, settling on the name Data Cloud. So today, when you hear about the Snowflake platform, it's synonymous with the Data Cloud. Looking at the basic architecture diagrams that have appeared in their documentation over the years does not really tell its evolution story because the pictures have remained fairly consistent, showing 3 layers, which I further simplify with the verbs manage, compute, and store. The layers are independent, but they communicate back and forth to complete tasks. I'll use a simple example to demonstrate. An analyst writes a SQL statement to query a database. The manage layer uses the SQL to build a query plan. The plan is sent to the compute cluster, and it contains a list of the data subset that's required. The request is sent to the store as a list of micropartition files that are needed. Copies of the files are sent to the compute cluster, and the query plan is used to produce a results set. Results are sent to the manage layer, which provides them to the analyst. It's easy to think of these layers as physical machines that have CPU, memory, and storage. But in fact, these are logical layers, not physical assets. Snowflake software communicates with software services that cloud providers expose, and these services control the actual hardware. Here's a good analogy. You live in New York and you buy a vacation home in Florida. You want to rent it out when you're not using it, but since you live so far away, you can't manage the house year-round. So, you employ a property manager to oversee daily operations, like maintenance requests, landscaping, and security. But you also need a service that provides an intuitive web interface for customers and notifies the property manager about upcoming rentals. When you say you're staying at an Airbnb, you know that the Airbnb company doesn't own and maintain the physical house. Likewise, when you say you're loading data into Snowflake, you should know that Snowflake is not like an old-school database server. Snowflake doesn't own or maintain hardware. In the olden days, input tasks that loaded data competed for the same physical resources used by output tasks that queried data. The beauty of the Snowflake system is that separate compute clusters can be used for the production and consumption of data. Like the Airbnb analogy, there are physical assets, services to manage the physical layer, and customer-facing services. Snowflake is the Airbnb of enterprise data. When they were creating a cloud database in 2012, Snowflake chose not to own and operate their own infrastructure because cloud providers already invented that wheel. What this means is that when Snowflake wants to release new features, they simply need to write new software. To see a pattern in its evolution, I'm going to quickly walk through Snowflake's major feature releases, and I'll assign each to one of these roles as the feature's primary beneficiary. We'll start with features that were released in 2016. Sysadmins benefit from improvements in concurrency. BI analysts benefit from faster repeating queries. Data management enhancements for fault tolerance and data recovery. And enterprise-grade security features for encryption, privacy, access control, and authentication. An engineering tool for data loading and data sharing between enterprises. Features for large clustered tables and for another form of result caching. A market for data providers and consumers, and internal data sharing within an enterprise. Improved performance for point lookup queries, and a new UI for querying and visualization. Data services in the marketplace, and functionality to call external services to run business logic developed in Java and to process unstructured data. Snowpark delivers the benefits of Spark without its complexities. New features limit the exposure of sensitive data. You can synchronize accounts across clouds and regions and better understand usage and costs. Apps can call Snowflake via a REST API. Snowpark advancements like using Python natively within Snowflake, including the open source packages in the Anaconda distribution, plus stored procedures and unstructured file processing. A new type of view to protect privacy, and auto-classification to detect personally identifiable information. Usage details to identify performance problems. Streamlit was acquired to simplify the creation of data apps. A service to accelerate large queries. Data pipeline features for incremental processing and for improving the developer experience. Unistore for analytics on transactional data and for joining transactional and analytical data. Developers can more easily build and deploy native apps. Engineers can work with iceberg tables. The SnowConvert tool was acquired to help customers migrate their databases, and an API enables Snowpipe to stream data. A tool was acquired and integrated to extract content from documents, and Snowpark features to improve model building and ML ops and to enable new workloads with containers. Here's a summary of what we just saw. In the early years, the focus was on improving data management capabilities. But during the 2020s, it was roles that work with data that saw the most new features, including the new consumers, data app developers, and data scientists. Of all the new features that I mentioned, the change that had the most impact was enabling each compute node to host the Python runtime system. Python is already used by many roles, like for these example tasks. The benefit of using Python inside of Snowflake is that data does not need to be copied to outside platforms. Data inside Snowflake is protected by a dome of security and governance features like encryption in transit and at rest, column and row level security, role-based access and control, and masking policies. During the early years with Snowflake, data engineers loaded and transformed data that BI analysts consumed. But today, more kinds of consumers run more types of workloads now that Snowflake is a platform.